Okay, so the plan for today is to just continue with differential equations. I posted a supplement on first order linear and an application or two of separable equations late last night. So that's available now. We'll cover the basics of second order differential equations. And then I'll probably post, I'm guessing we won't get all the way through second order equations. So I'll post another supplement finishing up any last little topics in diff EQ, some second order equations, maybe a little discussion of Euler's method, as well as some material from chapter 8. So just a little bit of wrap up stuff from chapters 8 and 9. I'll post in the next couple of days. The Unit 2 exam will work very similar to the Unit 1 exam. Sample exam posted in the next couple of days. And that's going to be this coming week. So the week of 3/11, that'll be the Unit 2 exam, just like the previous one. You can take it anytime during that week. And, you know, the Unit 2 exam, there'll be a sample exam for it. It'll be very similar to the actual exam, similar length and so on. I think the sample exam is available now on WebAssign. I don't have the tab up, but I think I posted it and made it available on WebAssign and sent out some information about that earlier this week. I have a whole bunch of classes with different midterm exam weeks coming up here, but I'm pretty sure I sent that out for Calc 2. So the plan for today is just to jump right into chapter 17. We're not going to cover all of chapter 17. We're certainly not going to cover all of second order equations, but we're going to focus on a particular subtype, second order linear constant coefficient homogeneous equations. So this is a lot of qualifiers, but in differential equations, typically the more qualifiers you have, the narrower the scope, and in some sense, at least, the easier the topic. So each of these qualifiers makes things a little bit easier for us to deal with. So we're really just kind of scratching the surface of second order equations. We should get a feel for this solution methods for second order equations, but we're certainly not going as deeply into them as we would in, say, a differential equations course. Okay, so consider, we're just going to look quickly at a motivating application. Consider a mass spring oscillator. So here we think we have a fixed point, and we have a mass of some sort that's on, let's say, just some wheels. We can think of these maybe like frictionless wheels. And we have a spring that is attached to the mass. If we pull the mass this way, say stretch the spring out from equilibrium, let it go, we know that the mass is just going to oscillate back and forth. When the spring is stretched, it wants to pull the mass back towards the fixed point. That creates some momentum. The mass will have some inertia, push past equilibrium, compress the spring, and then the compressed spring will want to push the mass away from the fixed point, and the cycle starts over. So let's suppose that we have an equilibrium point, say y equals 0. And we're interested in knowing y of t, the position at time t, the one-dimensional position at time t of this mass. We're going to consider influences of the spring as well as friction and inertia. And I'm not going to go through all the details here. This is just a motivating example, but we can look at Hooke's law, for instance. The force of the spring is proportional to the y component, the y value, just the deviation from equilibrium. We'll choose to model the frictional force as being proportional to y prime. So if we're traveling twice as fast, we encounter twice the frictional force. We might, in other cases, choose to model frictional force as something like y prime squared. But here we're sticking with y prime. There could be some other external forces, maybe we're, pushing the mass along or pulling it or something like that. We could have a forcing term. If we equate my double prime with all the forces from F equals ma Newton's second law, and we rearrange, we end up with this equation. M, B, and K are constants. We could have an external force. F external, the external force could be 0 also. So here, M, B, K are constants. M is not 0, otherwise this would be kind of a goofy setup where for some reason we don't have any inertia in the system. And the external force could be 0, could be something else. So let's consider a couple of special cases. We'll take 0 for the external force. We'll also consider B equals 0, so no damping, no friction, no air resistance. And this gives us a second order equation. My double prime plus ky equals 0. If we were to rewrite this, we would see that y double prime equals negative k over my. If I forget about the constants for a minute, let's just say k equals m. Drive physicists crazy by saying k equals m. Don't say things like that in physics class, but in math, we would just say that, k and m just kind of go away. Y double prime equals negative y. Do I know of a function or functions that the second derivative is negative of the function? Well, that sounds a lot like trig functions, like sines and cosines. So if I think of something like y of t equals cosine of t, then y double prime is negative y, and that's what we want. We do, however, need to fix some constants. We do actually want to get out of k over m. So how can I adapt this solution so that y double prime is negative k over my? Well, I need to take two derivatives. I need to pop out a constant twice. I need to get a constant squared being k over m. If I put a root k over m inside of my cosine, I think that will do the trick. So again, we're starting off here. We have a pretty straightforward problem, and we can basically just brute force the solution, or at least a solution. So the solution is going to look like a cosine function, or a solution is going to look like a cosine function. I put in a degree of freedom omega, and I choose omega to be root k over m, and this gives me a solution. I note that the frequency increases, my mass goes back and forth faster if I have a stiffer spring. And I note that it decreases with mass. So I have a heavier mass, it's going to move more slowly. Right? If k is larger, we get faster oscillations. If m is larger, we get slower oscillations. Again, we're not going through an algorithm yet. We're not going through this super procedurally yet. We're just looking at a motivating application. We missed an underline here. There we go. Case 2, if we take b not equal to 0, but still no external force. And let's take these values for m, b, and k. M equals 1, k equals 25, b equals 6. Again, this is our equation up here. So we need to solve this second order equation. And this is probably one where you wouldn't be able to reasonably guess the solution. If we tried to do something like y double prime equals negative 6y prime minus 25y, it's not going to work out so nicely, right? If I guess something like y equals cosine of t, y double prime is like cosine of t. So that seems to mesh, but then y prime is like sine of t, and getting that sine to work with the cosines it doesn't seem very promising. Turns out that the solution is going to look more like this. Or I keep saying the solution. I should be really properly saying a solution. Y equals e to the negative 3t cosine of 4t. I can think of this as two pieces. I have a cosine bit that's causing an oscillation, and I have an exponential bit that's kind of, in a sense, acting as the amplitude of that oscillation. So this e to the minus 3t looks like this. The cosine bounces between plus and minus 1. So e to the minus 3t cos of 4t is going to bounce back and forth between these two kind of guiding lines here. So I get what are called oscillations with damping. Qualitatively, this makes sense. I have friction and air resistance now. Maybe I have a little bit of rolling friction from the wheels or some air resistance as my mass is moving. So every pass that it makes, say the spring is stretched and it pulls it back towards the fixed point, a little bit of that energy that was stored in the spring is going to be sapped. It's going to be dissipated into the environment as maybe heat energy, maybe a little bit of sound energy, something like that. So it's going to compress the spring a little less than it had stretched it. And then when the spring's compressed and it pushes it away from the fixed point, it's going to, again, lose a little bit of that energy to the surrounding environment, and it's not going to stretch it as far as it was stretched before. So my oscillations die out over time. In theory, I keep oscillating forever, but the oscillations get smaller and smaller and smaller. And then what happens if I have a similar setup for the size of the mass and the stiffness of the spring, but if I have a larger friction term, if I am pulling my mass through a thicker fluid, maybe instead of air, it's through water or something like that. Or maybe my, axles for my tires, the grease is really gunky and it's just making a lot of friction. If I look at an example like this, y double prime plus 10y prime plus 25y, changing this 6 to a 10 actually completely changes the nature of the solution. A solution is just something like y equals e to the minus 5t. In other words, my spring, when it's stretched, is not powerful enough to overcome the fluid that it's trying to pull the mass through. It just kind of gradually pulls the mass back to equilibrium. It can never impart enough force. It can never provide enough energy to overcome that frictional force and come back to equilibrium with some inertia still and surpass equilibrium. So we lose all oscillations in this case when the frictional force is high enough. So we looked at 3 scenarios. In all cases, the external forcing term was 0. And we looked at no frictional force, maybe something like a moderate amount of frictional force, and a larger amount of frictional force. Okay, so let's consider a differential equation of this form. Here, A, B, and C are constants. So we said a second order, linear, constant coefficient, homogeneous differential equation. So A, B, and C are constants. So that's the constant coefficient part. the equals 0, or in other words, the no explicit dependence on t, the independent variable, is the homogeneous part. The second order part, why is it second order? Because we have a second derivative as the highest number of derivatives. And why is it linear? That's a little bit more complex. That's a little bit more complicated to think about. But let me give myself a little extra room here. So the last qualifier that we have to talk about is linear. Why is this a linear differential equation? This is actually a very important part of what we're going to be doing here, is the linearity, the linear nature. Remember that a linear operator, let's say O of ax plus by, it splits sums apart and constants can come out. Right, the derivative of af plus bg is a derivative of af prime plus bg prime. Same with the integral. These are linear operators. So that's what that's the context that I'm thinking of here. Let me consider a case where I have two solutions. To this equation. Maybe one of the solutions is like y equals cosine of t, and the other one is like y equals sine of t. In particular, I want two solutions that aren't like terms, because if they're like terms, they're just basically the same solution. So we might call these linearly independent solutions, but essentially we want two solutions that are unlike terms. T versus t squared, they would be unlike terms, but like, 3t and 4t, well, those are just the same solution, basically. Well, what if I take a linear combination of these? Is this a solution? Well, let me not use a and b. I forgot that a and b were used in my differential equation. We use different letters, alpha and beta. So if I take some linear combination, some number times the first solution plus some number times the second solution, and I make a new function out of that, a combination of these original two solutions, is that also a solution? For this linear differential equation, it is, and that's why we call it a linear equation. Why is that? Well, a times y double prime is alpha y1 double prime plus beta y2 double prime plus by prime plus b alpha y1 prime plus beta y2 prime plus cy. I want to know, is this equal to 0? If it is, then I found another solution that's a combination of the original two solutions. And I see that I can factor out all of the alpha stuff. That takes care of these three terms. And I can factor out the beta from all the beta stuff. Is this 0? Well, remember, I know that y1 is a solution to the differential equation. So a y1 double prime plus b y1 prime plus c y1 does equal 0. And the same for y2. So this is a linear differential equation because if I find two solutions to this differential equation, a linear combination of those solutions is also another solution to this differential equation. I'm going to make pretty heavy use of that throughout this discussion. Can we find a general strategy? Can we get an idea of how we might want to go about finding solutions to equations like this? Let's try to do what we kind of did above, where we write y double prime in terms of the other components. So what am I looking for? I'm looking for a function whose second derivative looks like a linear combination of its first derivative and itself. In other words, I need a function whose derivative and second derivative are also like terms. Like terms. The derivative, second derivative, and the function itself are all like terms. If I started with something, if I took a guess of like y of t equals like t to the fifth, well, the derivative is t to the fourth, the second derivative is t to the third, more or less. Those are unlike terms. Doesn't seem likely that something like that is going to be a good candidate function to guess for the solution of this type of equation. Something like a sine or cosine gets us closer, but we have the issue that the second derivative and the original function work nicely. Those are like terms, but the first derivative is the other one. If I start with cosine, the first derivative is sine, and those don't combine very well, and vice versa. But I do have a pretty nice candidate function, the exponential function. Roughly speaking, its derivatives itself and its second derivatives itself, and you can't get much more like a like term than just being yourself. So maybe a good candidate function to use is an exponential function of some sort. Can I guess maybe y equals maybe e to the t? Well, if y equals e to the t is a solution for some choice of a, b, and c, then it's almost certainly not going to be for a different choice. I need to add a degree of freedom in here. I need to have a parameter in my guess, in my model, that I can pick or that I can tune or adjust depending on the exact differential equation I'm looking to solve, depending on what a, b, and c are. If I do something like put a constant in front, well, then y prime is exactly equal to y double prime is exactly equal to y. That doesn't really help me either. But if I put a constant in the exponent, this gives me kind of just enough complexity. Not so much additional complexity like y equals e to the t squared or something that the derivatives aren't like terms. The derivatives are still going to be like terms, but I have a parameter that I can now tune. I can now choose r based on a, b, and c, and maybe try to fit this model to an individual differential equation. So y prime, and y double prime are all going to play nice together. But I do have maybe just enough complexity that I can fit my model, my guess, to the differential equation I want to solve. And that's what I've kind of written out down here. But let me just go through it kind of by hand. If this is my guess, y equals e to the rt, if I want to plug into this differential equation up here, what does that look like? A y double prime plus by prime plus cy equals 0. Now, I don't know, at this moment, I don't know if this guess is going to actually work or not. It might not work, but if it does work, then this has to be true. I notice I can factor out an e to the RT. And I know that e to the stuff is never going to be 0. So I end up with this relationship relating R to A, B, and C. I have a quadratic equation in R such that AR squared plus BR plus C has to be 0. How should I choose R to make this work? Well, it's going to be negative B plus or minus root B squared minus 4AC all over 2A. Or it's going to be negative B over 2A plus or minus root D over 2A, where D is our discriminant. So what are my solutions to R going to look like? I have 3 cases for my roots of my quadratic equation based on the discriminant. If the discriminant's positive, the thing under the square root is positive, then I end up with 2 distinct real roots. If the discriminant is 0, I end up with a repeated root of multiplicity 2 of negative b over 2a. And if my discriminant is less than 0, well, then I'm square rooting a negative number that yields complex roots. These are my 3 different cases that I could end up in. So for right now, we'll cover the first 2 cases. And then the complex case works a little bit differently. So that will probably be part of the supplement, I would guess. But we'll see how far we get. One other little note up here is that in this type of equation, there's always a trivial solution. Y of t equals 0 is a solution. Typically, that's not the solution that we're really looking for or interested in. This is what happens to the system if you just set the mass at the equilibrium point of the spring and give it no initial velocity. It just kind of sits there forever. But if we either stretch the spring and let it go, or if we sit at equilibrium and give it a push, or if we do both, then it's going to start, bouncing back and forth or doing something like that. Those are the interesting solutions that we're typically looking to find. Okay, so let's look at some examples of the first case, the most straightforward case with 2 distinct real roots for R. So again, we have our guess. Y equals e to the RT. Y prime is R e to the RT. Y double prime R squared e to the RT. If I plug this into my differential equation, I know an e to the RT is going to factor out. I have a 1 R squared minus 1 R minus 2. Remember, Y is just e to the RT, so this last term here doesn't get any R's in it. And that's equal to 0. This tells me R squared minus R minus 2 equals 0, or R minus 2 r plus 1 equals 0, which says that r equals 2 or r equals -1. So I have two solutions, two candidate solutions. One associated with r equals 2, y equals e to the 2t. Maybe we'll call this y1. And another associated with the other root -1, y2 equals e to the -t. Each of these functions would solve the differential equation just fine. Now, one thing that we might be thinking of is, well, if I think about this, kind of theoretically, if I take a step back from the details, I say, even though I didn't explicitly do this, what have I done to get rid of two derivatives? I've kind of done two integrals. Whether that's kind of behind the scenes or explicitly done, I got rid of two derivatives. I essentially did two integrals. Where are my arbitrary constants? This is where that linearity comes in. Remember, because we have the equals 0 over here, as well as each of these terms just being like a y or a derivative of y. I don't have like a y prime squared or something like that, or a sine of y or something like that. This is a linear equation, which means that if I find two solutions, a linear combination of those solutions, constant 1 times y1 plus constant 2 times y2, will also be a solution. I could combine these two solutions together to get another solution. Maybe I'll call it A, e to the 2t plus b, e to the -t is also a solution. By the linearity of this differential equation, I found two independent solutions, two solutions that are not like terms. I can't combine together a term like e to the 2t and a term like e to the -t. I can take a linear combination of these two solutions, a e to the 2t plus b e to the -t. That also will be a solution. And in particular, it's a solution for any choice of big A and big B. We see that if we picked big A equals 0 and big B equals 0, we get the trivial solution y equals 0. If we picked big A equals 1, big B equals 0, we get y1, or one of our fundamental solutions. And same thing if we chose big A equals 0, big B equals 1, we get y2. But we could also choose big A equals 1 and big B equals -10, or we could get a bunch of other solutions from here as well. And it's not just a solution. It turns out that it's the most general solution. So a function that looks like this for any choice of A and B will be a solution to the differential equation. But we can also say the opposite of that. Any solution to this differential equation will be of this form. There will be some choice of big A and big B that matches that solution. We kind of proved the one direction, we didn't prove the other direction, that every solution of the differential equation will be of this form. But again, we're not going into as much detail as we would in a full differential equations class. So this would be the most general solution. We do see our two arbitrary constants coming from those, at least behind the scenes, those two integrations. We didn't explicitly do any integration, but in theory, we kind of did. We see our two arbitrary constants coming from those two integrations, getting rid of those two derivatives. So what about an example like this one? Y double prime minus 4y equals 0. We might even be able to guess the answer to this one. Y double prime equals 4y. Well, let's go through the motions. Here we'll guess y equals e to the rt. Y double prime then is r squared e to the rt. I have 1r squared minus 4y, so that's just minus 4. It could be tempting to put like a minus 4r here or something because we see the y and we like want to put something there, but y is just e to the rt, and I've already factored that out. I know e to the rt is never 0. That's an exponential function, always positive. That means r squared minus 4 has to be 0, r squared has to be 4, or r equals plus or minus 2. My two component solutions, e to the 2t and e to the negative 2t. And then again, because of the linearity of this differential equation, I can take a linear combination of these. Any function of this form will be a solution of the differential equation, and any solution of the differential equation will have this form. This is the most general solution. Of this differential equation. Again, there's not a good reason to maybe initially suspect that this would be the most general solution. We didn't like algorithmically go through and derive the solution. We made a guess that we thought was a good guess. Who's to say that sine t or cosine t or something won't work? But it does turn out that this is the most general solution for this differential equation. What if we had an initial value problem like this, where we have a differential equation, y double prime minus 3y prime plus 2y equals 0, with some associated conditions. Remember, our solutions to the differential equation are families of functions. That's true in first or second order. In first order equations, it's a family of functions parameterized by one arbitrary constant. So we need one constraint to determine that one arbitrary constant. In second order equations, we have two arbitrary constants. We need two constraints, typically an initial position, y of 0, and initial velocity, y prime of 0. We need two initial conditions to determine those two arbitrary constants. So this might be something like the initial position of the mass on the mass spring system and its initial velocity. So it's starting at a position that stretches the spring by 2 units, and it also has a velocity in the direction of stretching the spring more, a velocity of 1 unit in that direction. Now, a little bit of a side note, this wouldn't be a very good physical system from a mass spring system standpoint, because we have like negative air resistance. So it's like if I'm moving forward, the quote air resistance pushes me forward even more. So not a very, the analogy does break down here because of that negative coefficient there, that -3. So the analogy breaks down when we get solutions. The solutions won't be consistent with what we would expect from an actual mass spring system. But we can, kind of see that we have an initial position and velocity needed here. And we can think of a mass spring system, its behavior is going to be different if I stretch the spring 2 units and push it to the left versus push it to the right versus don't push it at all initially. Okay, so what do we do here? Well, we first solve the differential equation, get the most general solution, and then we figure out what are the values of the arbitrary constants to satisfy the constraints. So we guess y equals e to the RT. This yields a characteristic equation. Y double prime is going to be r squared e to the RT. We know that e to the RT is going to end up going away. Minus 3y prime is going to have one factor of r. Plus 2y has no factors of r equals 0. I see that I have r minus 1 times r minus 2 equals 0. So r is 1 r2. My component solutions, y1 is e to the 1t, y2 e to the 2t. My most general solution, taking a linear combination of them, I missed a t up there. Y2 is e to the 2t. So y equals a e to the t plus b e to the 2t is the most general solution to the differential equation. And now I want to impose my two conditions. What's y of 0? On one hand, it's got to be 2. On the other hand, it's a plus b. What's y prime of 0? On one hand, it's got to be 1. On the other hand, it's got to be, well, y prime is just a e to the t plus 2b e to the 2t, a plus 2b. If I subtract the second equation minus the first equation, a minus a goes away, 2b minus b is b, and 1 minus 2 is negative 1. B has to be negative 1. And I want something minus 1 to give me 2. A has to be 3. So I just solve this 2 by 2 system, whatever way you want to solve it. I used the addition method and then plug back in. And I combine these pieces of information, my solution to the full initial value problem, the function that solves the differential equation and also meets the two initial conditions. You got to make sure the right number goes with the right function. So 3e to the t minus e to the 2t. This, put two boxes around it, I guess. That's the full solution to the initial value problem. So the hard part is really solving the differential equation, then a little bit of algebra to get the initial conditions matched up correctly. Any questions so far? Okay, so we have this kind of almost like a magic trick, making it this educated guess of an exponential. And that worked pretty nicely for the two distinct real roots case. We have two other cases though. So let's take a look at what happens in this case, discriminant 0, where we have one repeated real root, one root with multiplicity 2. So let's again guess y equals e to the RT. Y double prime is going to be r squared, e to the RT. We know that's going to factor out and then go away. minus 2y prime. Y prime is going to have one factor of r plus y, but y is just e to the rt, so I just get a plus 1 equals 0. Or this is r minus 2 squared equals 0. We get only a single root of 2 with multiplicity 2. In a sense, I kind of have like y1 equals e to the 2t and y2 equals e to the 2t. If I tried to really force the issue, really what I just end up with is, since I have like terms, they just kind of collapse down to one term, and I really only end up with truly one arbitrary constant. Or another way to think about it is, even if I left it in the A and B form, I wouldn't be able to meet two initial conditions. I wouldn't be able to meet an initial position and an initial velocity, because A and B are just basically one. There's just basically one constant A plus B. But I don't want to throw out what I already did. I mean, I did get one solution here. That's valuable. The question is then, how do I find a second, what we call linearly independent solution? How do I find a second solution that is not a like term with the first solution? And the answer is that in this case, in the case where we have a repeated real root, this doesn't work in the last case. If you tried this in the last case, the thing you'd come up with as a candidate solution wouldn't work. But in this case, if we multiply by a factor of t, this works. This gives us our second solution. Again, we're not going deeply into why this is true. One way to see that it's true is just to actually plug it in and show that it's true. There is a way to kind of derive the second solution based on the first one. It's called reduction of order. But again, we're not getting into all of that. So, I mean, it seems like I just pulled this out of thin air, and to be fair, I kind of did. But this is, in this case, where we have a repeated real root, our kind of first fundamental solution is the one that we would expect to get. And our second one is that same solution, just with a t in front. These are not like terms. I can't combine, 3 e to the 2t plus 5t e to the 2t. Those don't combine as a single term. These are unlike terms. I can now construct my most general solution. I can construct my most general solution by taking a linear combination of these. Again, these don't collapse into a single term now because of that factor of t. That factor of t, like I said, it's a very specific thing. If I put a t squared or a square root of t or something in here, it wouldn't work. If I went up here and said, does y3 equals t e to the 2t work? It's not going to work for this case. It's something specific to this special case, discriminant 0. We get one fundamental solution from our characteristic equation. We get the second one by multiplying by the independent variable, and that gives us the second independent solution, just in this special case. So this is the most general solution to the differential equation. In this case, I do have some initial conditions. I would like, in some sense, an initial position of 2, initial velocity of -1. Again, we don't really have nice correspondence with a physical mass spring system here because of the negative middle coefficient. So, we're going to get answers that are going to be discordant with something like a mass spring system. But I'm saying things like initial position, initial velocity, because that's kind of how we typically think of them. So what's y of 0? Well, the t here, the factor of t actually makes this even easier. The whole b term goes away. On one hand, y of 0 is a, and on the other hand, that has to be 2, so that takes care of that. What's y prime of 0? On one hand, it's got to be 2a. And then what do I get here? If I differentiate the t, I get b e to the 2t, so that's plus b. And then if I keep the t but differentiate the other stuff, because I kept the t, if I plug in 0, that whole term just goes away, right? So I did do a product rule, but the term that keeps the t from the product rule, we plug in 0, that zeroes it out. The term that loses the t, we get an e to the 0 times b, that's just b. So 2a plus b has to be -1. Or 4 plus b equals -1. B has to be -5. And so this is the most general solution to the differential equation. And the solution to the initial value problem that satisfies the constraints as well is y equals 2e to the 2t minus 5t e to the 2t. Any questions on that? I'm going to skip the proof of this, but basically the proof just relies on the repeated root. Where was it? Up here? It relies on the repeated root when the discriminant is 0. The root is -b over 2a. Having that specific choice for the root, -b over 2a, you get a bunch of stuff that kind of cancels out nicely whenever we have this extra factor of t in here. It pops out a whole bunch of extra junk from the derivatives, from the product rules. But all that product rule stuff cancels out nicely because r equals b over 2a. And then, so the product rule stuff cancels for that reason. And then the kind of vestigial e to the rt stuff cancels because this is a solution. So it's important that we have just the factor of t here, which makes the product rule stuff cancel correctly, and that we're using the original solution because that's what the other side of the stuff, all that has to zero out. That zeroes out because of the y equals e to the rt being a solution to the original differential equation. If you wanted, to do an exercise, you could work through and prove this claim. But just for the sake of time, I'm going to move on to this last problem. Okay, so we have one more problem. Y double prime minus 6y prime plus 9y equals 0. Y of 0 is 2. Y prime of 0 is 9. So again, I guess y equals e to the rt. Y double prime is going to be r squared e to the rt. Y prime is going to be r e to the rt. Y is e to the rt. That whole thing gets factored out and divided out, and then we're just left with that 9. So I have r minus 3 squared equals 0, or r equals 3 as my repeated root. So y1 equals e to the 3t. This is the case where I have a repeated real root. The way that I generate y2 is by multiplying by t. y2 is t times e to the 3t. And my most general solution to the differential equation is a e to the 3t plus b t e to the 3t. And again, I have an initial value problem. I want to meet some initial conditions. Y of 0 on one hand is just a, and on the other hand, that's got to be 2. And similar to above, y prime of 0, that's going to be 3a. And differentiating this second term, I differentiate the t, gives me b e to the 3t. Plugging in t equals 0 gives me just the b. And then differentiating the exponential leaves behind the t the factor of t. When I plug in 0, zeroes out that term. And 3a plus b has to be 9, or 6 plus b is 9, b is 3. So in blue here, we have the most general solution to the differential equation. This is the family of functions that satisfies the differential equation. Combining these three together gives me the solution to the initial value problem. Y equals 2e to the 3t plus 3t e to the 3t. Or if you wanted to, I suppose you could factor out the e to the 3t. You could write it like that as well. Any questions on this one? Or anything we talked about so far? We will leave the complex case for, we'll leave that for a supplemental video. We will run into imaginary numbers and complex numbers here. We'll have to use Euler's formula. So there are some additional complexities here, but all of the complexity having to do with the imaginary numbers is kind of behind the scenes complexity in order to generate this form of the solution. So as far as actually solving these equations, you can write down that in the discriminant less than 0 case, this is the form of the general solution, and then you just have to figure out what some of the parameters and constants and things are. So to solve the differential equation, practically speaking, you don't need imaginary numbers, but philosophically speaking, how do I get to this general solution? Why should the general solution look like that? That's where the imaginary numbers come in. Imaginary numbers are closely tied in many mathematical contexts to oscillations. So these oscillatory solutions are the result of having imaginary numbers or complex numbers pop up.